Are you coming to play more tonight?
Am I coming to what?
Play more.
No. But since they started doing that, the tops to bottoms and bottoms to tops, I can't wear my short shorts and cut off shirt anymore. So I just decided I won't come. All right. I just haven't. I didn't. When I wrote that up, I hadn't written it up yet. Sorry to destroy your weekend. All right. So before we start talking about exponential functions, let's just a recap of what we have done. We just finished talking about polynomials. First semester we talked about trig functions. And today we're going to talk about, in chapter 3, we'll talk about exponential and logarithmic functions. So when that happens, these functions, these families of functions, are the three basic families of functions that you'll use in 90% of all the math that you do. So these are really the foundation of pretty much everything else you'll do with math. So it's kind of nice because we will have hit every kind of function that we'll need. The trig functions and the exponential functions we call transcendental functions. So a lot of calculus books that you'll see will say Stewart's calculus, blah, 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 early transcendentals. And that means you do calculus with the transcendental functions early on in the book. The polynomials, the reason it's called transcendental function as opposed to a polynomial, which is an algebraic function, is we call the solutions to polynomials algebraic numbers, and the solutions to these kinds of functions turn out to be transcendental numbers. They're different kinds of numbers. Anyway, for today, we're going to talk about exponential functions. Exponential function is going to be something that looks like this. F of x equals a to the x. We want a greater than 0. And we also want a not equal to 1. What would happen if a was 1 for this kind of function? What's 1 to a? It would always be 1, right? It wouldn't be very interesting. We just have a constant. And x is any real number. So this is the kind of function that we're going to talk about for the next few, well, for this chapter, which is it's a short chapter. But this is what we're going to be talking about. We good here? Okay. So now we need to talk about their graphs. We want to know what they look like. I know graphing is everyone's favorite topic. So we have f of x equals a to the x. The domain of an exponential function, we can plug in any number we want into an exponential function. So all real numbers, negative infinity to infinity. The range goes from 0 to infinity. One really nice thing about exponential functions, oh, I forgot to say one other thing up here. A is called the base. One really nice thing about exponential functions, if we're not shifting them in any way, they always, no matter what the base is, it has a y-intercept at the point 0, 1. So no matter what the base is, doesn't matter what this number is, we're going to get this as an intercept. And that's because no matter what a is, a to the 0, anything to the 0 power is 1. So they always cross the y-axis at 0, 1. Exponential functions have a horizontal asymptote. At y equals 0. So the x-axis is a horizontal asymptote for exponential functions. Our function is increasing everywhere. We say from negative infinity to infinity. And its range, decreasing we're increasing if a is greater than 1. So far, if this number is bigger than 1, and f of x is decreasing from negative infinity to infinity if 0 less than a less than 1. So what we're saying here is a is a fraction between 0 and 1. The graphs of exponential functions are pretty simple, which is one thing that makes them nice to work with. The graphs are easy. So what I want to do next is take a look at a couple of graphs, because all the graphs are essentially the same, and we'll talk about some applications of exponential functions. Exponential functions are really important. They model population growth, radioactive decay. They model investments, so that you end up using them for lots and lots of things. Another thing that's really interesting about exponential functions is if you let the exponent be a complex number, you get trig functions. So exponential functions become trig functions if the exponent is complex. And then you can use exponential functions instead of using trig functions to model things like electricity, like a circuit where the voltage is varying, something. You can use exponential functions to talk about that. You can use exponential functions to talk about light going through lenses. So it's kind of interesting. There's a connection between exponential functions and trigonometric functions. Well, let's look at the graphs. So let's graph an easy one. F of x equals 2 to the x. So our base is 2 here. Exponential function is really easy to graph. So we'll make a little sketch here. Put some. So we have a horizontal asymptote. We always have a horizontal asymptote if it's unshifted at y equals 0. Our graph is always going to go through, if it's unshifted, through the point 0, 1. And then to get the shape, we'll plug in some other numbers. So I'm going to say f of negative 2 is 2 to the negative 2. And what's another way I can write 2 to the negative 2? as a fraction. What is 1 over 2 squared? Negative exponent in the numerator, it's a positive exponent in the denominator, is 1/4. So we get the point negative 2, 1/4. So I get a point down here. F of negative 1 is 2 to the negative 1, which is what? 1/2. So I get a point at 1/2 there. And then we already have our intercept, our y-intercept there. So let's do f of 1 equals 2 to the first, which is just 2. And f of 2 is 2 to the second, which is 4. So I get a point up there. And my graph looks like so. And any exponential function is going to look more or less like this. Always increasing. The domain, negative infinity to positive infinity. The range, 0 to infinity. Always goes through this point, 0, 1, until we start shifting things. So a really, really easy function to deal with. All right, questions on that one? All right, let's do one more graph, and then we'll talk about how these graphs shift. So f of x equals, for this one, 2 to the minus x. Now this next little bit is really important to remember. I can rewrite 2 to the minus x, same thing that we did up here. I can write that as 1 over 2 to the x. And I can write that as 1/2 to the x. So 2 to the minus x is the same as 1/2 to the x. So this gives me my base being a fraction. So now, based on what we said before, this should be a decreasing function. Rather than increasing, we should have a decreasing function. So let's sketch a graph of that. We're still going to have a horizontal asymptote at y equals 0. We're still going to go through this point 0, 1. That doesn't change. And now let's calculate some values here. So I'm going to do f of 2 equals 2 to the minus 2, which we said was 1/4. So here I get a point down here. F of 1, 2 to the minus 1, 1/2. So I get a point there. We already have our y-intercept. F of negative 1 is 2 to the first, which is just 2. And f of minus 2 is 2 to the second, which is 4. So you point here at 4. And my function ends up, the graph of my function ends up looking like so. Decreasing, always going downhill as we go from left to right. Domain still negative infinity to positive infinity. The range still 0 to infinity. And we still have the same intercept there. So we could use something like this to model a population maybe that's increasing. Here we could model a population that's decreasing, or some radioactive decay maybe, something that's going, decreasing in amount. And our graphs of any exponential function is going to look more or less the same as this. Always have the same kind of curve, always go through this same point, always have the same horizontal asymptote. All right. We good there? Transformations. Shifting graphs, shifting exponential graphs of exponential functions is really easy. They shift just like any other function. The only detail that we have to keep in mind is that our intercept, the y-intercept, and the asymptote shift with the function. So if we're shifting our function left and right, because our asymptote's horizontal, that doesn't change that asymptote, but it's going to shift that intercept. The point that's at 0, 1, we shift it right, it's going to shift right, shift it left. And if we shift up and down, our horizontal asymptote's going to shift the same as the function, down the same as the function, and that intercept is going to shift up or down along with the function. So let's say, for example, I'm not going to sketch a lot of graphs because all we have to do is shift the intercepts and the asymptote, the intercept and the asymptote. I just want to kind of give a reminder about shifting functions. What if our parent function is 4 to the x? So that's our parent. What kind of shift would f of x equals 4 to the x plus 2 give us? What would it be? Now remember, this is with our x, so it's like with our vertex form of a parabola, this is the part that's with the x in parentheses. So the part with the x shifts us left or right, right? So this one, because x is positive, is going to be left 2. So that point, the horizontal asymptote still stays at y equals 0, but our intercept, the point that was at 0, 1, is going to shift over to negative 2, 1. So that intercept would shift up, or sorry, shift left 2 units along with the function. How about f of x equals 4 x plus 2 minus 3? So what's that going to do to our function? Left 2, down 3. So for this one, our horizontal asymptote would shift down 3, and then our intercept would shift left 2 and down 3 along with the function. How about f of x equals minus 4 to the x? Well, what is that? It's going to reflect. So we got that part over which axis? X. Reflect over x-axis. So then our asymptote, because it is the x-axis, that's not going to change, but our intercept would reflect over the x-axis. And then f of x equals 4 to the minus x. What is that going to do? go back here. Here's 2, and here's 2 to the minus x. What happened to these two graphs? Reflected over the y-axis. So putting a negative in front of our exponent reflects us over the y-axis. So that's exactly what happened here. Reflected over the y-axis. So sketching graphs of exponential functions is a lot easier than sketching graphs of other kinds of functions. We just shift our intercept and our asymptote along with the function. All right, questions there? Okay, one of the applications, one of the big ones that we'll talk about with exponential functions is compound interest. Compound interest is, I don't know, it's kind of what makes the world go round. That's how people make money. Compound interest. So let's say we start with an amount that we call the principal P, and we have an interest rate R, annual interest rate. So we're earning interest once a year on this principal. So after a year, we're going to say our amount after 1 year is the principal that we started with plus the interest we earn on that. And the interest we earn is the principal times our interest rate. So I want to develop this, to show you where this formula comes from. I can factor out that P, and I get P times 1 plus R. The amount after 2 years is the amount that we end up with at the end of the first year, P times 1 plus R, plus the interest we earn on that amount, which is P times 1 plus R times R. Well, now we have a common term of P times 1 plus R. So I'm going to factor that out. And when I factor that out of here, I end up with a 1. When I factor that out of here, I just end up with an R. And that gives me a P times 1 plus R squared. After 3 years, I end up with the amount that I had after 2 years, plus that interest that I earn on that amount, which is P times 1 plus R squared times R. Now I can factor out that P times 1 plus R squared times 1 plus R, which is P times 1 plus R to the third. And looking at this pattern, what's going to happen after n years? How much are we going to have? P times 1 plus R to the n power. So our interest, our compound interest, is an exponential function. So this is how we develop the formula. This is why it ends up turning out to be an exponential function. Now, usually compound interest, there's a little more to it than you earning interest once a year. So I want to write the formula that we're going to use for compound interest when you have a little bit more going on. Everybody good with where our formula is coming from and why it's an exponential function? Okay. So our compound interest formula. So for our formula, we're going to say P is our principal. R is the annual interest rate. N is the number of compounding periods per year. And what we mean by compounding is that's how many times you earn interest per year. So the formula we did before, we were just earning interest once a year. What else do I need to? What else do I need to have here? Annual interest rate. T is a time in years. And A is the amount that we end up with. So our formula for compound interest, our amount equals the principal times 1 plus R over N to the NT power. So the example we did before, N was 1, so we just ended up with a 1 here and a 1 there. And an interesting thing happens. We'll go through. I want to do show you how we do a couple of calculations with this. Interesting thing happens as N, our compounding periods gets bigger and bigger and bigger and bigger. All right, questions on the formula? Okay. So let's say we have $5,000. We get 6% annually, and we invest for 10 years. We want to know how much we have and we're going to calculate it for several different compounding periods. Annually. So if we're compounding annually, what is N? N equals 1. 1 compounding period per year. So our amount, the way we calculate, is going to be 5,000. 1 plus, we write our interest rate as a decimal, 0.06 over 1, which is 1 times 10. And then we would calculate this in our calculator. Remember your order of operations. Parentheses first, so we do this part in parentheses, exponent, and then multiplication. And if I calculate this out, I get $8,954.24. So I'm just plugging this into my calculator. So not a bad return for 6% for 10 years, compounded annually. Compounded, now we're going to do quarterly. N would be, how many compounding periods per year would we have here? 4. We end up with 4. So that's going to be 5,000. 1 plus 0.06 over 4. To the 4 times 10 power. If I calculate that out, $9,070.09. So a little bit better, compounding quarterly. Monthly, so N is going to be 12. Compound 12 times per year. And we get a little more money that way. $9,096.98. And then finally we'll do daily. So that's going to be n equals 365. And we calculate that out, and I get $9,110.14. So what do we see here? It keeps going up, but does it go up at the same rate? It slows down as we compound more frequently. And something interesting happens. We could compound minutely. We could compound once a second. We could compound twice a second, once every 1/10 of a second. So when mathematicians, whatever, bankers, people that were dealing with financial people were calculating compound interest when they first started working with compound interest, they found this interesting thing happen. As you compound it more and more frequently, this number that you get inside the parentheses here gets closer and closer to a certain number. So the quantity 1 plus 1 over x to the x power, this part in the parentheses, approaches this number that we call e. It's our special exponential base, which approximately equals 2.7, is it 7182? E is a number like pi. It's an irrational number. Not the decimal, it's a non-repeating decimal. So this quantity inside the parentheses gets closer and closer to this number e. This quantity raised to the n power, as x gets closer to infinity. So as we compound more and more and more frequently, we get what we call continuously compounded interest. And what that means is we just, as soon as our interest is compounded, we compound again immediately. So this number 365, the denominator here, and this number here, just gets bigger and bigger and bigger and bigger. We're doing it more and more rapidly until we're doing it constantly. We're constantly compounding our interest. Well, this 1 plus 1 over x to the x, this 1 plus our r over n raised to the n power, gets closer and closer to this number e. And our formula turns into the amount is p e to the RT. You've probably heard that before, PERT. You might have calculated interest with PERT before. And everything else is the same. P is our principal, R is our annual interest rate, T is our time in years, and E is this special number, 2.71828, da 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 da. And if you look at your calculator, you have a special button on your calculator that says e to the x, because this number e comes up a whole bunch in math. So if we calculate this interest, if we compound this interest continuously, we would get a equals 5,000 times e to the 0.06 times 10. And if we calculate that out, I'd get $9,110.59. So a little better than compounded daily, but not a huge amount better than compounded daily. So this would be our continuously compounded interest, and the other one is just our compound interest. All right, questions? I have a quick question for you. Biannually, what would be our compounding rate? 2? Biannually? 2? Semi-annually? So biannually is once every how many years? 2. So what would N be? 1/2. Semi-annually would be twice a year. So if we're compounding semi-annually, we're compounding twice a year. If we're compounding biannually, we're compounding once every 2 years. I think those come up in the homework. Semi-annual and biannual. All right, no questions? Exponential functions, probably, other than lines, probably the friendliest functions there are. I will tell you about, in my geometry classes, I give algebra review worksheet once a week, and one of the questions was write an example of an irrational number, and one student wrote a story about how 2 was dating 3, and then 2 and 3 broke up, and 3 got really mad, and how that meant that 3 was irrational. I wasn't sure whether to count it right or wrong. Yeah. I guess it would depend on whose side you took in the breakup, right? On 81 through 84, you should do without calculator. Use what you know about exponents. Just number 81 through 84, do without your calculator.